Vector diagrams are useful for understanding electrical systems, including single-phase loads on three-phase systems. Let's consider a balanced three-phase system with a line-to-line voltage of 208 volts and a single-phase load connected between one line, load, and neutral, and we'll assume the load is purely resistive. In a vector diagram, line voltage, VL, is represented as a vector with a magnitude of 208 volts, pointing horizontally to the right. Phase voltage, Vp, is represented as a vector with a magnitude of 120 volts, pointing vertically downward. This represents the voltage between load and N. Load current, IL, is represented as a vector with an unknown magnitude. It points to the right parallel to VL since the load is purely resistive. To determine the magnitude of IL, we can use the formula given. IL equals KVA divided by 208 volts times 1.154. In this formula, KVA is the apparent power of the single-phase load. 208 volts is the line voltage. 1.154 is a correction factor. The correction factor of 1.154 accounts for the fact that the load current is the vector sum of the currents in the three phases of the three-phase system. Because the load is connected to only one phase, its current is not directly proportional to the line voltage. A correction factor of 1.154 is used to adjust for this. The resulting vector diagram shows the line voltage, VL, as a horizontal vector, the phase voltage, Vp, as a vertical vector, and the load current, IL, as a vector pointing to the right, parallel to VL. The magnitude of IL can be calculated using the formula. The reason why a correction factor is needed can be understood by considering the current flow in each phase. Without the single-phase load, the three-phase system is balanced, meaning that the current in each phase is equal in magnitude and 120 degrees apart in phase. When a single-phase load is connected, it draws current from only one phase, disrupting the balance. This imbalance creates circulating currents in the other two phases, which affect the overall current distribution. The correction factor accounts for these circulating currents and ensures that the calculated load current is accurate. To elaborate further, let's consider the power calculations in a balanced three-phase system. The total apparent power, S, in a balanced three-phase system is given by the formula S equals the square root of 3 times VL times IL, where VL is the line-to-line voltage and IL is the line current. In a single-phase system, the apparent power is simply given by S equals V times I, where V is the voltage and I is the current. When a single-phase load is connected to a three-phase system, it draws power from only one phase, but the system as a whole must still be balanced. This means that the power drawn by the single-phase load must be compensated for by changes in the currents in the other two phases. The correction factor of 1.154 arises from the geometric relationships between the phase voltages and currents in a three-phase system. It represents the ratio between the line current in a loaded phase and the current that would be drawn if the load were distributed equally across all three phases. The specific value of 1.154 is derived from the square root of 3 divided by the square root of 3 over 2, which is approximately 1.154. This factor essentially adjusts for the fact that the single-phase load is only utilizing one phase of the three-phase system, and the current in that phase is higher than it would be if the load were balanced across all three phases. It's important to note that this correction factor applies specifically to single-phase loads connected between one line and neutral in a three-phase 208/120 volt system. For other configurations or voltage levels, the correction factor may be different. The use of vector diagrams helps to visualize the relationships between voltages and currents in a three-phase system with a single-phase load. By representing these quantities as vectors, we can easily see how they interact and how the correction factor accounts for the imbalance caused by a single-phase load. In summary, the KVA to amps calculation for a single-phase load on a three-phase 208/120 volt system requires a correction factor to account for the imbalance in the system. This correction factor, 1.154, adjusts for the fact that the single-phase load is only utilizing one phase of the three-phase system and ensures that the calculated load current is accurate. Vector diagrams provide a visual representation of the voltage and current relationships, helping to understand the need for the correction factor. Now let's delve a little deeper into the practical implications of using this formula and the vector diagram. When calculating the required ampacity of conductors and of current protection for a single-phase load connected to a three-phase system, it's crucial to use the correct formula that incorporates the 1.154 correction factor. Failing to do so could lead to undersized conductors or overcurrent protection, which could result in overheating, equipment damage, or even a fire hazard. For instance, let's say we have a single-phase load of 5 kVA connected to a 208/120 volt three-phase system. If we were to incorrectly calculate the load current without the correction factor, we would use the simple formula I equals kVA divided by volts, which would give us 5000 divided by 208, which equals approximately 24.4 amps. However, using the correct formula with the correction factor, we have I equals kVA divided by 208 volts times 1.154, which gives us 5000 divided by 208 times 1.154, which equals approximately 20.83 amps. As you can see, there is a significant difference between the two calculated currents. The incorrect calculation would lead to selecting conductors and overcurrent protection based on 24.4 amps, whereas the correct calculation indicates that 20.83 amps is the appropriate value. This difference could have serious consequences if the conductors and overcurrent protection are not adequately sized for the actual load current. Furthermore, the vector diagram helps to visualize how the single-phase load affects the overall balance of the three-phase system. By analyzing the vector diagram, we can identify any potential issues, such as excessive neutral current or voltage imbalances, that may arise due to the single-phase load. In cases where the single-phase load is a significant portion of the total load in the three-phase system, it may be necessary to take additional steps to mitigate these issues, such as balancing the load across all three phases or using a phase balancing transformer. It's also important to consider the type of load being connected to the system. Formula and correction factor discussed here apply specifically to purely resistive loads. For inductive or capacitive loads, the power factor must be taken into account, and the calculations become more complex. In such cases, it's necessary to use more advanced vector analysis techniques to accurately determine the load current and the impact on the three-phase system. Furthermore, the National Electrical Code (NEC) provides guidelines for calculating the ampacity of conductors and overcurrent protection for various types of loads. It's essential to consult the NEC and follow its requirements to ensure that the electrical installation is safe and compliant with local regulations. For example, NEC Table 310.15b16 provides ampacity ratings for various conductor sizes based on insulation type and ambient temperature. These ampacity ratings must be directed for factors such as high ambient temperature, multiple conductors in a raceway, and continuous loads. In addition, NEC Section 210.20 requires that overcurrent protection devices be rated at not less than 125% of the continuous load plus the non-continuous load. These requirements are designed to prevent overheating of conductors and overcurrent protection devices, which could lead to equipment damage or fire hazards. In summary, the KVA to amps calculation for a single-phase load on a three-phase 208/120 volt system requires careful consideration of the correction factor, the type of load, and the applicable requirements of the NEC. Using the correct formula and following the NEC guidelines is essential for ensuring the safety and reliability of the electrical installation. Vector diagrams can be a valuable tool for visualizing the voltage and current relationships in the system and identifying any potential issues that may arise. Now, let's consider a more complex scenario where the single-phase load is not purely resistive but has a reactive component, meaning it has both resistance and either inductance or capacitance. In this case, the power factor of the load comes into play. The power factor, expressed as a decimal or percentage, represents the ratio of real power, measured in kilowatts, to apparent power, measured in kVA. A purely resistive load has a power factor of 1, while inductive loads have a lagging power factor and capacitive loads have a leading power factor. When dealing with reactive loads, the formula for calculating the current becomes more complex. The apparent power, S, is still calculated as S equals volts times amps, but the real power, P, is calculated as P equals volts times amps times the power factor. To find the current, we can rearrange the formula to I equals S divided by volts, where S is the apparent power. However, we must also take into account the angle between the voltage and current, which is determined by the power factor. Vector diagrams become even more useful in this scenario. The voltage is still represented as a vector, but the current vector is no longer parallel to the voltage vector. Instead, it is shifted by an angle equal to a power factor angle. For an inductive load, the current vector lags behind the voltage vector, while for a capacitive load, the current vector leads the voltage vector. The magnitude of the current vector is still determined by the apparent power and the voltage, but the phase angle must be considered when analyzing the overall system behavior. The correction factor of 1.154 that we discussed earlier is still applicable in this case, but it may need to be adjusted based on the power factor of the load. The exact adjustment depends on the specific configuration of the system and the type of load. In some cases, it may be necessary to use more sophisticated techniques, such as symmetrical components, to accurately analyze the system. Furthermore, the presence of reactive loads can have a significant impact on the voltage regulation of the system. Inductive loads tend to cause voltage drops, while capacitive loads tend to cause voltage rises. If the reactive load is a significant portion of the total load in the system, it may be necessary to install voltage regulation equipment, such as capacitors or reactors, to maintain the voltage within acceptable limits. The NEC also provides guidelines for dealing with reactive loads. NEC section 220.18 requires that the load be calculated based on the volt-ampere rating of the equipment, rather than the wattage rating. This ensures that the conductors and overcurrent protection are adequately sized for the apparent power, which includes both the real power and the reactive power. In addition, NEC section 460 provides requirements for the installation of capacitors, including overcurrent protection, disconnecting means, and discharge resistors. These requirements are designed to ensure the safe and reliable operation of capacitors in electrical systems. In summary, when dealing with single-phase loads that have a reactive component, it's essential to take into account the power factor, the phase angle between voltage and current, and the impact on voltage regulation. Vector diagrams become even more valuable in this scenario, allowing for a visual representation of the voltage and current relationships. The NEC provides guidelines for dealing with reactive loads, ensuring the safety and reliability of the electrical system. Let's further examine the implications of unbalanced loads on a three-phase system, particularly when a significant single-phase load is present. In a perfectly balanced three-phase system, the currents in each of the three phases are equal in magnitude and 120 degrees apart in phase. However, when a single-phase load is connected between one line and neutral, it draws current only from one phase, creating an imbalance in the system. This imbalance can have several negative consequences, including increased neutral current, voltage imbalances, and increased losses in the system. The neutral current in a balanced three-phase system is ideally zero, as the currents from the three phases cancel each other out. However, when a single-phase load is present, the currents no longer cancel out completely, resulting in a non-zero neutral current. This neutral current can overload the neutral conductor, causing it to overheat and potentially create a fire hazard. The NEC specifies the minimum size of the neutral conductor based on the expected neutral current. NEC section 220.61 provides guidelines for calculating the neutral load for various types of loads, including single-phase loads. In some cases, it may be necessary to increase the size of the neutral conductor to accommodate the increased neutral current caused by the single-phase load. Voltage imbalances can also occur when a single-phase load is present on a three-phase system. The voltage in the loaded phase may drop, while the voltage in the other two phases may rise. This voltage imbalance can negatively affect the performance of other equipment connected to the system, particularly three-phase motors. Voltage imbalances can cause motors to overheat, reduce their efficiency, and shorten their lifespan. The National Electrical Manufacturers Association, NEMA, provides guidelines for the maximum allowable voltage imbalance in three-phase systems. NEMA standard MGUN specifies that the voltage imbalance should not exceed 1%. Voltage imbalance is calculated as the maximum deviation from the average voltage divided by the average voltage. If the voltage imbalance exceeds the NEMA limit, it may be necessary to take corrective actions such as balancing the load across all three phases or installing a voltage regulator. Increased losses in the system can also occur due to unbalanced loads. The unbalanced currents cause increased current flow in the conductors, which results in increased I2R losses, where I is the current and R is the resistance of the conductor. These losses can reduce the overall efficiency of the system and increase energy costs. To minimize the impact of unbalanced loads, it's important to distribute the load as evenly as possible across all three phases. This can be achieved by carefully planning the electrical installation and connecting single-phase loads to different phases. In some cases, it may be necessary to use load balancing equipment, such as phase balancing transformers or static VAR compensators, to improve the balance of the system. In summary, unbalanced loads can have several negative consequences on a three-phase system, including increased neutral current, voltage imbalances, and increased losses. It's important to distribute the load as evenly as possible across all three phases and to take corrective actions if the imbalance exceeds acceptable limits. The NEC provides guidelines for calculating the neutral load and sizing the neutral conductor, while NEMA provides guidelines for the maximum allowable voltage imbalance. By following these guidelines and implementing appropriate load balancing techniques, it's possible to minimize the impact of unbalanced loads and ensure the safe and reliable operation of the three-phase system. Let's now discuss the practical considerations for mitigating the effects of single-phase loads on a three-phase system, focusing on techniques for load balancing and voltage regulation. Load balancing involves distributing the single-phase loads as evenly as possible across the three phases of the system. This minimizes the neutral current, reduces voltage imbalances, and improves the overall efficiency of the system. There are several techniques that can be used to achieve load balancing. One common technique is to connect single-phase loads to different phases in a systematic manner. For example, in a multi-story building, the lighting circuits on one floor could be connected to phase A, the lighting circuits on the next floor could be connected to phase B, and the lighting circuits on the third floor could be connected to phase C. This helps to distribute the load evenly across all three phases. Another technique is to use a load schedule to track the loads on each phase and identify any imbalances. The load schedule should include all of the single-phase loads connected to the system, as well as their expected current draw. By analyzing the load schedule, it's possible to identify any phases that are overloaded and to redistribute the loads to balance the system. In some cases, it may be necessary to use load balancing panels or automatic transfer switches to automatically balance the load across the three phases. These devices monitor the current on each phase and automatically switch loads to different phases to maintain balance. Voltage regulation is another important consideration when dealing with single-phase loads on a three-phase system. Voltage imbalances can cause equipment to malfunction or overheat, so it's important to maintain the voltage within acceptable limits. There are several techniques that can be used to improve voltage regulation. One common technique is to use capacitors to compensate for the reactive power drawn by inductive loads. Capacitors generate reactive power, which helps to offset the reactive power drawn by inductive loads and to improve the power factor of the system. Another technique is to use voltage regulators to automatically adjust the voltage on each phase. Voltage regulators are typically used in applications where the voltage fluctuations are large or where precise voltage control is required. In some cases, it may be necessary to use a combination of load balancing and voltage regulation techniques to achieve the desired performance. For example, in a data center, it's important to maintain both load balance and voltage regulation to ensure the reliable operation of the computer equipment. In addition to these techniques, it's also important to properly size the conductors and overcurrent protection devices to ensure that they can handle the expected load current. The NEC provides guidelines for sizing conductors and overcurrent protection devices based on the type of load and the operating conditions. By following these guidelines, it's possible to ensure that the electrical system is safe and reliable. In summary, mitigating the effects of single-phase loads on a three-phase system requires a combination of load balancing and voltage regulation techniques. Load balancing helps to minimize neutral current and voltage imbalances, while voltage regulation helps to maintain the voltage within acceptable limits. By implementing these techniques and following the guidelines of the NEC, it's possible to ensure the safe and reliable operation of the electrical system.